So welcome back, everybody. I just wanted to give you some very few messages before we move on to the exercise solutions. And some of the messages about small hints and tips about solving the exercises. And you will see here that at the end of the slides, the weekly slides, we have some kind of small hints on how you can solve some of the Taylor exercises, which especially this on the rocket. And then I wanted to say something about one of the most used algorithms for solving this type of equations, which we have in project number 9 in homework number 5. And this is called, in the literature, it's called the velocity-Belay method. And it's a kind of standard when you're solving equations like in material science, people use something which is called molecular dynamics in order to simulate atoms and molecules. And then this method is one of the most used numerical methods ever. So we are just going to move on with the some small hints and tips about the exercises. And then we just, could you please, hello? Could you just comes into the recording here. Okay, so let me just quickly say something about the, exercise 2 and 3. And you will find a hint at the end of the slides for this week. So let's just bring that down. And this recording will be available as normal. So let me just bring up the exercise number 2 and 3. So I just wanted to say something very briefly about how you would proceed. And sometimes when you read the exercises, you have this kind of feeling, where do I start? How do I actually solve the exercises? So parts of the exercise is actually almost solved in the textbook. So you have a kind of guidance on how to do it. So what you would typically do in this exercise is that you have a rocket with a specific mass m, and there's made an assumption that this mass has some kind of time dependence. So it loses mass with a kind of constant times time. And the mass, if you use momentum conservation, it's now given by the mass times the velocity. And then you have the mass when it misses, the rocket misses a mass delta m. And then there's a reminder here. So what's done there is simply to set up momentum conservation. So that's the first stage in solving that exercise. Then what you have is just a manipulation of the equations. And you see now that what is normally done is that you skip the terms which go with delta m times delta v. When you multiply out here, you will see that there is a term delta m times delta v, this term multiplied with that one, which, as you can also see in the textbook, you assume that that is small. So you just drop it, because this would be 2 corrections. So this is a typical trick, or an approximation, which you would often do when you're looking at equations. And that simplifies also the mathematics, because else things would have become much more difficult. So what you would get then would be something like this. So you skip this term, and then you reorder it. And then you simply multiply, you assume now that delta v goes to a very small dv, and delta m does the same. So you want to look at some kind of instantaneous change. You multiply and divide with dt. So you would have dv here, which is a change in velocity. And then you have dm divided by m. And then what you do then is to integrate up. So you would assume now that you have an initial velocity, which is 0, because you assume that the rocket was at rest. You put that to 0. And then you start with an initial mass m0. And then you end up with a final mass m. And now you have an integration in terms of m here. And when you do that, this is just a log. So you would simply then get a velocity here, which is given by this constant, times this log of m divided by m0 here. which is the initial mass of the object. And then you plug in this mass here, and then you would have an equation like this, which gives you the velocity. That's without the gravitational acceleration. Then you can simply add the gravitational acceleration, which is just a constant, right? So that would give you another term, which goes like minus g times t here. And that means that your velocity would look like what you have at the end here. So yeah, go ahead.
Means that the exit velocity,
yeah,
or escape velocity,
yeah, exactly. So the sometimes it's a little bit difficult to understand where the exercise wants you to go, but if you look into the text as well, I mean, you can get quite some guidance on how to go ahead. Then in the next exercises, you are asked to find the position. And what you need then, since you now have the velocity, is that you can integrate that up as a function of time. And if you do that, that's a standard procedure. So you have the velocity as a function of time, then you will simply integrate from a time t equals 0 to some final time. So what you would need to do next, if you now look at the integral which you have to solve, you would start with some initial position, which you can put to 0. And then you need to plug in that expression for the velocity which you found, and then integrate it up. Now, that's going to involve an integral with the logarithms. And in the next slide, for this weekly, of this weekly slides, you will see how you can actually solve that integral. Now, remember now that when you're solving these exercises with integrals, you're free to use Mathematica. You're free to do it by paper and pencil if you prefer that, or other symbolic packages. So it's not the way you arrive to it which is important. It's actually more the way you've been thinking, and then you can analyze the answer afterwards and discuss what it means. So if you then go to the final one, you would have to calculate an integral like this. And in case you have forgotten it, and I hope you don't get offended if I bring up all these details, this is more to remind you of the kind of tricks you would use in order to solve that kind of integrals. So everything is in the weekly slides. So you can look it up whenever you want, and see if you agree with the developments and if that matches what you have done in these exercises. So that was a small hint about the two of the exercises. The other thing I wanted to do is actually to give you this recipe for the algorithm, which is one of the most used algorithms in simulations of Newtonian-like equations, where you have energy conserving forces. And that's the velocity-Verlet algorithm, which strikes a balance between numerical accuracy and the number of CPU cycles you want to invest in. So if you wish to program that one, it involves a slight modification with respect to the Euler-Kromer method, but it's not a big complication. And if you look back at what Julie talked about on Wednesday, about code reusability, you can easily make a small function which does the velocity-Verlet algorithm for you. So let me just show you the algorithm, because we didn't do that on Wednesday, and that's where I'm going to stop. So then George and I, we will move around and discuss the solution of the homework with you. And Julie is going to assist those of you which are online here. Okay, so let's do this final thing, which is the velocity-Verlet algorithm, because you will find that extremely useful when you're solving differential equations. So let's do that. So that's the missing piece from Wednesday. And the reason we bring it up is that it's a method which is easy to code. And you're going to encounter this in possibly in many, many other applications of this kind of Newtonian-like systems. So let's go through it. And everything is based on you manipulating Taylor expansions. It's nothing more than that. So this is a famous method in numerical mathematics and in physics applications. And it's a pretty simple method to implement. And I just wanted to point out some of the details which you need to look at. So everything starts with a Taylor expansion. So what we have been doing is that we have stopped at the first term, the delta t, which is given by the derivative with respect to time. And then what we are going to do now is to actually move on a little bit. So we're going to have a derivative with the second derivative with respect to time of dt. And then the error now comes at the level of d delta t cubed. So when we did Euler's method, we simply stopped here. That's the simplest possible thing we can do. Now, if you look at the equation here, we can now rewrite this in terms of x of t. That's the previous time step. And then we have a delta t, but we know what dx dt is, right? Anyone remembers that? That's a famous quantity which we are calculating here. The velocity. So we would have the velocity. So this is v of t. And then we keep the next term, delta t squared, divided by delta 2. And then the second derivative of the x, or the position in general, that's another quantity which we see again and again. Acceleration, fantastic. So what we would have now is a of t. Okay, so that's the first part. And then we discretize this the way we're going to write it as a code. So we discretize, and then we have x of I plus 1, which is equal to x of I plus delta t, the velocity at time I, plus this delta t. So now we have actually a correction in time, which goes one stage further. And hopefully, this is going to give us better results. So when you deal with this Taylor expansion, there's always a truncation you have to make. If you stop at the delta t, then you're just back to Euler's method. Now, the other quantity we are interested in is the velocity, because we are integrating up velocity and we are integrating up positions. So when you deal with classical mechanics, it's always about this. We want the position and the velocity of some kind of object under the influence of some forces. So the next quantity we need is just the velocity. So we would do the same thing, Taylor expand again. So we would have a v of t, and then we do a delta t, and then we have the dv dt. And then we have the higher order terms, delta t squared. And then we have the second derivative of velocity of dt plus a delta t of O of delta t cubed. And we are going to approximate that one to the second power in terms of v of t, no, delta t. So we have delta t here. And now dv dt, that's something which we also know, right? And that is the acceleration. Fantastic. I'm not listening to music, by the way. So that is a of t. So we know that one, and that's which we should have from the forces. And then we would have a delta t squared divided by 2. And now we have the second derivative of dt. Now, this is something we don't have. We don't have an expression for that. So we would need this would be the derivative of the acceleration with respect to time. Yeah?
That's sometimes called the jerk.
Say it again.
Isn't that sometimes called the jerk?
Yeah, that's correct. Yeah. But when we don't know something, if you now look at the last term, the dv the second derivative velocity, this term here is actually this first derivative of the acceleration, right? Now, we have the forces, and unless the force depends on time, we don't know how to evaluate this quantity. So when we have the gravitational force, for instance, this depends on the position, and the positions depends on time. So this becomes complicated. So when we want to approximate something numerically, and we don't know what to do, what do you think is the simplest possible way to approximate this derivative? Euler's method. When we don't know what to do, we just use Euler's method. And this is what is done here. Excellent, excellent. So this is what we would do then is simply to approximate this with a of I plus 1 minus a of I divided by delta t. And this is nothing but Euler's method. And you will see this again and again in all numerical algorithms. So one of the things I want to, in a way, to demystify is the simplicity of many of these numerical methods. And when we look at the ways to solve differential equations, it's often you cooking up some kind of Taylor expansion. So what we end up with then, when we plug that in, when we discretize it, we get a velocity v of I plus 1, which is equal to v of I plus delta t times a of I. And then I have plus delta t squared multiplied with a of I plus 1 minus a of I divided by delta t. And when I then rewrite it, this is going to be given by v of I plus delta t divided by 2. And I have a of I plus 1 plus a of I. And this is the velocity-Vallée algorithm. Now you have to pay attention to one thing when you're calculating it now. So if we bring everything up, so let's frame it in. So we have x of I plus 1, which is equal to x of I plus delta t of v of I plus delta t squared divided by 2 of a of I. So we need to calculate that one. And in the next step, we're going to put this one here, v of I plus 1 is equal to v of I plus delta t divided by 2 of a of I, a of I plus 1. Plus a of I. So if you now look at the equations which you have here, there are two things you need to pay attention to. So this acceleration feeds in here, but you need to calculate the new acceleration based on the new position. So you need an intermediate calculation here in order to calculate the acceleration at the new stage. So a of I plus 1 needs this quantity here. So there's going to be a function of f of x of I plus 1, which calculates the acceleration. So if you're dealing with a gravitational force, you would need to calculate the acceleration again with a new position before you can update the velocity. So you cannot calculate the velocity first. You have to calculate the position first, and then you do the velocity. So that means that compared to Euler-Kromer, which is very simple, this needs an intermediate step, but it gives a better precision because Euler-Kromer has a mathematical truncation which goes like delta t. This has a mathematical truncation which goes like delta t squared. And that gives better results and more stable results. And it strikes a compromise between accuracy and number of calculations which you need to do. And you will be surprised to see that this is actually one of the basic workhorses in simulations of materials. New medicines, for instance, you use the velocity Valais algorithm to simulate systems like that. Somebody gives you a potential surface or potential energy, you calculate the forces, and then you plug it in to this solver here. So for people doing that type of calculations, this is actually one of the basic algorithms. And you should feel free to use that one. Or if you think Euler-Chroma is the most painless way you can do things, you can use that one as well. Yeah, go ahead.
Is there any way to combine the two?
Not these two, but you can actually modify Euler-Chroma to something which is called the Richardson algorithm, which has a kind of delta t squared. But it gives an asymmetry in velocity and position. So the thing with the velocity Valais is that velocity and position have the same error in delta t. And that's why people would favor them. Okay, I'm going to stop here. And feel free to look at the hints for exercises at the end of the slides. And then George and I, we are just going to circulate around and raise your hands, ask as many questions as you want. Feel free, never hesitate to ask questions. Yeah, see, I have a hand there. I'm coming. I'm just switching off the video and then. No, so this is plus A of I. Because what you have is a minus A of I here, delta t, but then you had a delta t before. So you had a term, if you now look at it, so that's a good question. So let me just do that. If you look at what you had here, you had a delta t squared divided by 2, but you have a minus A of I here, but you have a plus here. So you have a delta t squared, the delta t there. So you get delta t divided by 2 minus, so that gives you a delta t half plus that. Excellent, thank you. More questions before we turn off the video here? Okay, so I'm just going to switch off the video and then feel free to ask questions.